In the last class, you remember just yesterday we did two things, right? So first, we talked about the free particle, right? And how to solve Schrodinger's equation for a free particle. And the calculations, were not terribly hard. They were easier than the other problems that we've done. But there was a problem in interpreting the results, right? That is that the wave function that came out was not normalizable. And I showed you my kind of workaround for dealing with that, with working in a finite system and then taking the limit as the system size goes to infinity. That sort of works, but there's a better way. And so in order to prepare you for the better way, I had to go into this math refresher about Fourier transforms. Okay, so that was the second half of the class yesterday. All right, so now that we have this math background, let's go back to the quantum mechanics of the free particle. Okay. So here, for the free particle, what we already found were the special separable solutions. That is the stationary states. Okay, and so these are solutions, right, of the form psi of x, the lowercase time independent thing, is just e to the I kx. Okay? And this solution has an energy, E is h bar squared k squared over 2 times the mass. And so the time-dependent solution is the uppercase psi of x and t. So it's the product, e to the I kx times e to the minus I energy t over h bar. Okay, so that's all well and good, except that we can't normalize it, right? We can multiply it by some coefficient, but there's no coefficient that we can multiply it by that that will make the normalization integral come out to be 1. Okay, so what do we do, right? Well, the idea here is that we want to consider a linear combination of these solutions. So you know that when we were doing the particle in a box, or when we were doing the harmonic oscillator, we could make a linear combination not for the purpose of normalization, but for the purpose of matching the initial conditions, right? So we've had a few problems like that. Okay, now let's do the same thing for both purposes, right? Both for the purpose of matching the initial conditions, but also I claim this will fix up the normalization too, as a good side effect. Okay, so let's see how that would work. Okay, so if we have a series of discrete states, okay, so that is states where you can count them, right? Like for the particle in a box, you have state number 1, state number 2, state number 3, etc. Right? If you have discrete states like that, then you know that you can combine them to get a general state. Let's call it psi general of x and t, which is a sum over this index n of a coefficient c sub n times psi n of x exponential minus I e n t over h bar. Okay, so that's what we've done a couple of times, and you've done it in your homework also. Okay, now what is very similar but slightly different here is that we have solutions that are characterized by the wave vector k, right? And k is continuous. That is, you can't just make a list of the allowed values of k, right? In a finite system, you can, but in the infinite system, you can't. In the infinite system, k can be anything along the number line, right? And so I can't just say, I'll add up something of this and this and this, right? But I have to say anywhere along the whole line, you can have some k. So that means that now instead of a sum over an index n equals 1 or 2 or 3, I have to have an integral over all the possible values of k. Okay? So I'm going to do something like that. Okay, I will say, if you have continuous states, then the psi general of x and t is not going to be a sum, but it'll be an integral. Okay, so an integral over k, so that sum turns into an integral. Okay? And the coefficient Cn has to turn into something that depends on k. So let's call that phi of k. And then the wave function, lowercase psi n, this thing, well, that turns into the special separable solution that we already calculated. So that is e to the I k x. And this exponential with energy times time, that is e to the minus I, and then the energy is h bar squared k squared over 2m. And that is multiplied by time and divided by h bar. So I'll cancel one of the factors of h bar in the numerator. Yeah. Okay. So this thing has to be integrated over k. So at the end, I write dk. And then it's kind of conventional to put a factor of the square root of 2 pi in the denominator. That's not a really important part, but that's a convention that people have. All right, so let's say that's conventional. So this is a way to combine states with different k's, with a whole range of k's, to make a single wave function, in the same way that an equation like this combines states with different n's to make a wave function. Okay. Now, we know that this linear combination satisfies Schrodinger's equation, right? So by analogy, you should believe that this combination satisfies Schrodinger's equation for the free particle. In case you don't believe me, let's check it and see. Okay, so let's check to make sure that this psi general of x and t satisfies our original Schrodinger equation. So the Schrodinger equation is I h bar d psi dt is equal to minus h bar squared over 2m, a second derivative with respect to x, plus v of x times psi of xt. And here, for this free particle, there's no potential energy. So that term goes away. Okay, so I want to take this psi, it's defined by an integral down there, and plug it into this Schrodinger equation and just check, is this true? Question mark. Is this true? Let's find out. Okay, so this is IH bar. Now we want the derivative of all that stuff with respect to time. Okay, so that is going to be an integral over k. We have the phi of k. Well, that doesn't depend on time. That's just a constant right there. We have the e to the ikx. That doesn't depend on time. And then we have the time-dependent exponential factor. Okay, so that is that does have a derivative with respect to time, right? We bring down negative I h bar k squared over 2m times this e to the negative I h bar squared k squared t over 2m dk over root 2 pi. Okay, so now we want to check, is this equal to what goes on the right side of Schrodinger's equation? Okay, so the negative h bar squared over 2m, and here we have an integral over k again, right? Phi of k, that doesn't depend on x. Now we need to differentiate the e to the ikx. Okay? So that gives us a factor of ik. It gives us two factors of ik because it's a second derivative with respect to x times e to the ikx, and then the time-dependent part, e to the minus I h bar squared k squared. No, not h bar squared. Excuse me. Just h bar. H bar. You knew that, but you just were not telling me, so you wouldn't embarrass me, right? Okay. So minus I h bar k squared t over 2m dk over square root of 2 pi. Okay, so is this equal? Right? Well, let's check, right? So the point is, I just want to take these factors in front and put it in there, right? And likewise, this factor in front and put it in there. Okay, so what I get is this integral. This is boring to keep writing all the time. IKX. I times negative I is 1. And so then there's h bar squared, k squared over 2m, k squared t over 2m dk over 2 pi. Okay, and so is this equal to the integral phi of k? All right, so putting the prefactor inside, there's an I squared times the k squared, so that's -1. That cancels the negative sign in the front. Okay? And then h bar squared, k squared over 2m, ikx, e to the minus I, h bar k squared t 2m. All right, yes. Yes, okay. So this combination of all these exponential solutions is indeed a solution of the Schrodinger's equation for a free particle. So it works for any function phi of k. Okay. So it doesn't matter what the phi of k function is, right? With any phi of k function, this will be a solution of Schrodinger's equation for a free particle. So then we can say, is it normalized? Okay, so this is what I was hoping to, the problem that I was hoping to solve. Okay. So let's check that. Okay. So we want to know, what is this normalization integral? Okay, so we want the 1 to be equal to the integral of psi star of x and t times psi of x and t dx. Okay, so let's work that out. This is going to be an integral. Let's see, first we have to put in what is psi star. Okay? So we have this expression for psi. We need to take the complex conjugate of that. Okay, so that means we need to take the complex conjugate of everything that's here. Okay, so as we go along, we'll need to do a complex conjugate of phi. That might be complex. And for sure, we'll need to change all of these i's, both of these i's, to negative I. So our psi star is going to be an integral of phi of k star e to the negative ikx e to the positive I h bar k squared t over 2m, like that, dk over root 2 pi. Okay, that is psi star. Now we need to write down psi. Okay, that's also an integral. That is the integral. Now, I would say it's an integral over k, but I just used the letter k over here. And if I'm combining two different integrals, I better use a different letter for whatever I'm integrating over. So I'll call it k prime instead of k. So an integral of phi of k prime e to the ik prime x e to the minus I h bar k prime squared t over 2m dk prime over the square root of 2 pi. Okay, so this thing is that, right? This thing is that, the psi of x and t. And all of this needs to get integrated dx. Okay, now we can simplify this integral, right? We simplify by changing the order of integration, okay? So I want to just to do the x integral because there are not so many things here that depend on x. So let's factor out the things that don't depend on x. All right, so I have an integral over k and an integral over k prime. Those things don't involve x. I have a phi star of k and a phi of k prime. Those things don't have x. I have the time-dependent factors, e to the I h bar k squared t over 2m. I have an e to the minus I h bar k squared k prime squared. There's a prime there. K prime squared t over 2m. None of those things depend on x. Okay, so what's left that does depend on x is an integral dx of e to the I k prime minus k x. Okay, so now I need to do this integral, right? So this integral, it depends on k and k prime, right? This is inside the k and k prime integrals. Actually, maybe I'll move it over to make it clearer. Can I actually just, ooh, that's so cool. Yeah, I'll put it over here. Okay, that makes it inside those integrals. All right, so now I'm going to do this integral. So, do you guys know how to do this integral? All right, this is an integral over x of the exponential I times something times x. Okay. What you get depends on whether the something, the k minus k prime, is 0 or not 0. If k minus k prime is equal to 0, then you are integrating 1, right? You're integrating 1 over all x from minus infinity to infinity. Integral is infinity, right? But if the thing inside the exponential is anything other than 0, then you have an oscillating function there. And then it cancels out, right? So what you have in this integral is infinity if k minus k prime is 0, or 0 if k minus k prime is anything other than 0. Right? So this integral turns into a Dirac delta function. It is 2 pi delta of k prime minus k. Do you guys know about the Dirac delta function? Is that something that you covered in your math classes?
Yes.
Yes, maybe a little bit. Okay. I'll talk about that in just a minute. Let me finish doing this integral, and then I'll talk about the Dirac delta function. Okay, so hold that thought. Okay. Dirac. Whoops. Dirac delta function. Okay, so this is all equal to, well, it's an integral dk over root 2 pi and integral dk prime over root 2 pi phi star of k, phi of k prime. And we have these exponential factors. K prime squared t over 2m, and then this 2 pi delta of k prime minus k. All right, the 2 pi's cancel, and we can do the k prime integral. All right, we do the k prime integral using the Dirac delta function, as I will talk about in just a minute. And the only contribution comes when k prime is equal to k. So we get still an integral over k, phi star of k, phi of k. And then these exponentials cancel, and that's all. Right? So this is an integral over k of phi of k magnitude squared. Okay, so it can be normalized, right? It's the wave function is normalized if we have a phi of k function such that this thing is normalized, right? And so this is possible. I'll say it can be normalized. It's possible to normalize this with a good choice of phi of k, although it's not guaranteed to be normalized for any phi of k. The Dirac delta function. Okay, let me take a minute to talk about that, because we're going to use it for other stuff too very soon. The Dirac delta function, okay, that's a function which represents a spike. Okay, so you could have some f of x as a function of x, which looks like it's 0, and then it goes up, goes up and over and down like that, okay? And let's suppose that the height here is h for height, okay? And let's suppose that the width here is 1 over h. Well, you're going to think that's Planck's constant. I shouldn't use it. I'll use capital H. Capital H. Okay, so the height is h, the width is 1 over h. Okay, so it goes from x equals 1 over 2h to x equals negative 1 over 2h. Okay. So the integral under this function, so the integral from minus infinity to infinity of f of x dx, well, that's equal to 1, right? You know it has to be equal to 1 because that's the area under this curve. Okay. So this is a nice function, and its integral is equal to 1 no matter what h is. Okay. So now we can say, let's take the limit as h goes to infinity. Okay. So I'm going to go to other functions that are even taller and narrower. Okay. So here's a function that's twice as tall and twice as narrow. The integral under that is still equal to 1. Okay. Then I'll go to something else that's even taller and narrower, like that. The integral under that is still equal to 1. Okay. So in the limit as h goes to infinity, I get a function which is infinitely tall and infinitely narrow. Okay. So in the limit, I get a function, well, I don't even have a good way to draw it. Here's x, okay, here's x equals 0. Okay, so I have a function which is 0, 0, 0, 0, 0, 0, 0, 0, infinity, 0, 0, 0, 0, 0, like that. Okay, that is the Dirac delta function. Okay, and so delta of x is infinity for x equals 0. It's 0 for x not equal to 0. And it has the property that the integral of delta of x dx is equal to 1. This thing is useful for lots of kinds of computations, and we'll have some examples coming up very soon in this semester. Well, it was useful just on the last slide, for example. Okay, and one way that it's useful is you could say, what if you are doing an integral and you multiply a delta function times some other function? Okay, so we could say for any function g of x, if we have an integral of g of x times delta of x, okay, that is equal to g at 0. Okay, and why is this true? Right? Well, because if you have the g anywhere other than at x equals 0, you're just multiplying by 0, right? It's multiplying by this delta, which is 0 in places other than x equals 0. Right? And so the only place where g matters is at x equals 0. Right? And then it's just multiplying the delta function. And so you get g of 0 there. Right? Or if you have an integral of g of x, and this is dx, of course, g of x times delta of x minus x naught dx, this is g of x naught, right? Because the only place where g matters is when x equals x naught. Now, this is stuff that maybe the math department supposedly taught you, though I'm not positive of that. But it's definitely useful in doing Fourier integrals like this. And so this place is one example of where it's useful, right? And so, you know, it is a known integral that this thing, the integral of this something times x, exponential of something times x, that's a little bit messy. E to the I k prime minus k times x, like that. This integral is 2 pi times that Dirac delta function, okay? And then whenever you have a Dirac delta function inside an integral, it makes the integral really easy, right? Because you don't have to do any complicated computations. You just have to recognize where the argument of the delta function is equal to 0, right? So that's what's happening here, right? If I'm doing the k prime integral, I have a delta of k minus k prime. No, k prime minus k. I have a delta of k prime minus k. That's like the delta of x minus x naught in the slide that I showed you before. Okay, so I'm integrating over k prime of something of k prime. All this stuff is like g of k prime times delta of k prime minus k. So the result of the k prime integral is all of this stuff evaluated when k prime equals k. So that this just goes there. This gets evaluated when k prime equals k, so it goes there. This gets evaluated when k prime equals k, and then it cancels this guy. Right, so that's how I did this integral. Is that making things clearer or less clear? I'm not exactly sure about this. Okay. If you think you studied this in a math class and you just don't remember very well, I want you to go back and look at your notes from that math class because I am going to be using it again. It's not just for this one calculation. I'm going to be using it again probably on Thursday for a different physics problem. Okay, so and if you think you've never heard of this and you want to discuss, what this whole concept means, you can ask me now, or you can ask me after class, or you can send me a secret message, and so that you don't have to tell anybody else. Any of those things are fine. I don't hear anybody asking me now. All right, so let's go on. Okay, so we have this nice expression for a general wave function, okay? That is this integral right here. Okay. So for any function, phi of k, it satisfies Schrodinger's equation for the free particle. So then if I put in any function phi of k, I can do this integral and get out some function of x and t. Okay, so that means you're wondering, well, okay, but how do I know what function phi of k goes here? And the answer is, it's just the same way that I know what coefficients Cn go there. That is from the initial conditions. Okay, the initial conditions determine these coefficients, as you know from your homework. And likewise, the initial conditions determine the phi of k function. Okay, so let's see how to do that. Okay, so if we want to determine phi of k from the initial conditions, that means we look at time t equals 0. So if I take my psi general and I just plug in t equals 0, this thing at x and time 0, okay? That is an integral of phi of k e to the I kx. And then the time exponential is e to the something times 0. That's 1. dk over root 2 pi. Okay. So someone gives you the initial condition. So someone gives you this function, okay? You want to find phi of k. Okay. To do that, you need to do the inverse Fourier transform, right? You can see that this expression, this is a Fourier transform integral, okay? And so if you, this is giving you a function of x from a function of k. If you want to go the other way, you already know how to do it from the rules of Fourier transforms, right? So to go the other way, you say phi of k is an integral of this psi general of x and 0 e to the minus I kx dx over root 2 pi. So someone gives you this initial condition. Okay. If someone gives you this initial condition, you can put it into the integral and do the integral, and you get this thing. You get phi of k. And then once you have phi of k, then you can put it into this psi general of x and time, and you can predict what the wave function will be in the future. And say, now this is phi of k, okay? You've got phi of k, right? You put it there. And So then you multiply it, e to the ikx, e to the minus I h bar k squared t over 2m dk over root 2 pi. And then you know what is psi at any future time. Okay? So the procedure is to start with the initial condition, put it into this integral to get the phi of k's, the same as you did integrals to get the coefficients in your previous homework. And then, in your previous homework, you put the coefficients into a sum. Okay, now you put the coefficients, you put the phi of k into this integral thing to get the wave function in the future. And then once you've got the wave function into the future, then you just do all the things we've been doing all semester. You can get the probability density in the future, or you can get expectation values in the future. Okay, so I want to show you a couple of examples of doing this in Mathematica. Let's see, are there any questions on the whiteboard before I switch over? Okay, let's see. So I'll switch to do. Oh, and I forgot to tell you a word for this thing. Here, I'll go back to the iPad just to tell you a word. The word for this thing is called a wave packet. That is a good vocabulary word, right, to mean a combination of waves like this. Okay? It is a combination of waves where there's not a single k, but you're integrating over a range of k. So let's see what that looks like in practice. Okay. So here is an example in Mathematica. Okay, actually I have two examples here. Is this good? Do you see the Mathematica? It doesn't show up on my screen. Yes, you do? Okay, good.
Yep.
All right, great. Then what? So we will, here is an example of a wave packet, okay? So here is an initial condition that I might give you, okay? So this is an initial condition of the exponential of minus ax squared, and I already normalized it, okay? So here's a plot of it, okay? You're already familiar with this function from the harmonic oscillator, right? So suppose this is the initial condition for the wave function of a free particle, okay? And now we want to know what's going to happen in the future, okay? So let's go through the series of steps, okay? So one step is, let's just check the normalization to make sure I didn't make a mistake, okay? Oh, good, the normalization is equal to 1, right? It is a normalized function, okay? So this whole procedure for making a normalized function works. Okay, so now that I have this initial function, I can calculate what's the phi of k. Okay, so I do that by doing this integral. Okay? So it's an integral of the initial condition times the exponential of minus ikx and integrated dx over 2 pi, over square root of 2 pi. for x goes from minus infinity to infinity. Okay, so here is the result. Okay, so Mathematica can do that integral. Okay, and the integral of the Gaussian in x turns out to be a Gaussian in k. Okay, that's a nice function. Let's make a plot of it. Okay, so here's a sample plot of that phi of k function. All right, so now we know the phi of k's. We know the energy as a function of k. That's this h bar squared k squared over 2m. Right? So then we can calculate what happens in the future. The psi in the future for any x and any time is going to be this integral. Okay, so that's the integral of phi of k times the exponential of ikx times this time-dependent factor integrated dk over root 2 pi. Okay, and luckily for me, Mathematica can do this integral also. Okay, and so I get this integral, okay, which is a function that depends on x and time. Okay, so I started with an assumption for what happens just at time t equals 0. And now by going through this whole process, I am solving Schrodinger's equation to predict what will be the wave function in the future. So it's like a classical mechanics problem where you start with the initial conditions for a particle moving and you predict what the particle will do in the future. Okay. So this is the psi, the wave function. The psi star is the complex conjugate of that. So here's the complex conjugate, okay? So it means that wherever there's an I in this expression, it's changed to a negative I there. Okay, so if I have psi and I have psi star, I can multiply them and get the probability density. Here's a probability density. Okay. I can check whether this probability density is normalized by just integrating it over all x. Yes, good. It's normalized, right? We had a proof of that, right, back at the beginning of the semester, right, that if you have a wave function that starts off normalized, it stays normalized. So here's an example of that, right? It starts off normalized and it stays normalized. Okay, so now let's do some cool graphics, okay? So let's see what happens if I make an animation going into the future. Okay. So this is an animation of the wave function. Okay. So the wave function is a complex number. So I have to plot both the real part and the imaginary part. Okay. So here, the blue is the real part. The orange is the imaginary part. Okay. So it starts off with the initial condition that I chose, where the wave function is all real. And then as I go forward in time, the wave function doesn't stay all real. It oscillates between real and imaginary as we go forward. And it all spreads out like that. So if we want the probability density, that is the real part squared plus the imaginary part squared. That's a real thing, right? And it spreads out, okay? So in this case, right, we have a probability density that starts off very concentrated at the origin, and then it gradually spreads out over a range of x. And then I can calculate averages, right? So the same as we've done lots of times in this semester, right? I can calculate the average x. It's always 0. That's not a surprise because everything looks symmetrical about 0, right? You can get the average x squared. It's getting bigger. That's not a surprise because you can see things spreading out. So the uncertainty in x is getting bigger as a function of time as the particle spreads out, right? Then I can get the average momentum squared. So the uncertainty in the momentum, okay? And then let's check the product of the uncertainty in x times the uncertainty in momentum. That is this combination, okay? So that is a half h bar times all this square root. You can see that right at the beginning time, this matches the limit from the uncertainty principle of a half h bar. As we go forward in time, the product is getting bigger and bigger. That's allowed by the uncertainty principle. Okay, so this is one example of what could happen with a free particle, right? You could start off with a state where the particle is centered at the origin at x equals 0 with 0 average momentum. And as a function of time, it just sort of spreads out. Okay? Now, let me show you a different example of something else that could happen. Okay? Suppose now I want something that has a non-zero average momentum. Okay, so here I'm making up another function. Okay, my new function is just like my old initial wave function, except that now I'm multiplying by this exponential of I k naught x. Okay? So there's this extra phase factor, which depends on x. Okay, let's repeat all the same steps for that wave function and see what it looks like. Okay, so if I plot the wave function at t equals 0, okay, here is some example where k naught is 10 and a is 1. You can put in your own numbers for some other example, right? You can see this looks like it has a whole bunch of oscillations, right? It looks like there's an envelope around here, but there's a bunch of oscillations up and down inside the envelope. Okay, so then what? I can check if it's normalized. Yes, good. Okay. I can do this Fourier integral to calculate what is phi of k. Okay. Mathematica can do that. It is, again, a Gaussian in k, but it's not a Gaussian centered at k equals 0. It is now a Gaussian centered at k naught. Okay, so here's an example of that, right? This is an example where the peak is here at k equals 10, but there's a certain width of the peak, like that. Right? And then we can predict what happens in the future, the same way as before. Okay, so we have our energy, so we can make the integral of phi of k times the position-dependent factor, e to the ikx, times the time-dependent factor, e to the minus I energy time over h bar, integrated dk over root 2 pi. And luckily, Mathematica can do that integral too. It may take a minute to do. Okay. Mathematica can do it. And here's the answer from when I calculated it before. Okay. And here is the complex conjugate of that. All right. So here is psi star times psi. Okay. So this is a nice function of position and time. It's a little more complicated than before, but it's some function of position and time. I can check if it's still normalized. Yes, it is. Okay. The integral of that thing comes out to be 1. Well, okay, there it is. It comes out to be 1. Now let's make a plot of that. Okay. So to make a plot of that wave function going into the future, a movie of that wave function, come on, it takes a moment. So this is the starting, okay, here it goes, the movie. The starting state, this is what I put in, right? This is what I put in, which has the envelope times a function that's oscillating up and down. Okay? And now you see, as this goes forwards into the future, it moves. Right? It doesn't look like it's just a particle that's staying in the same average position. Now it looks like the average position is moving forwards. And it's also spreading out as it moves. Okay. So now you can see why it's called a wave packet, right? It looks like, you know, Amazon made a package of a bunch of waves, and then they deliver it from here over to there, right? And so this is the package getting delivered, right? It's all moving somewhere, and it's moving at some velocity. How about the probability density? Okay, so if we multiply psi times psi star and make a plot of that, okay? So this is a real thing. It starts off peaked at x equals 0, and then it gradually moves, okay? So here is the wave packet moving. So you can't see all the oscillations up and down, but you can see the envelope that moves from one side to the other, okay, and spreads out as it moves. So we can calculate averages again, okay? We can calculate the average of x in our usual way, right? With this integral sandwich, and we get an average x that's now proportional to time, okay? So that's like, you know, what you know from university physics, right? For a classical particle, right? That if it starts off moving with some initial velocity, then the x is going to be proportional to time. And there's an average x squared, like this. So there's an uncertainty in x, which is gradually increasing. Likewise, there's an average momentum, which is now not equal to 0. Okay, so this is a case where we construct the integral sandwich with psi star and then the momentum operator minus I h bar d by dx acting on psi. And we do this integral, and the integral is not equal to 0, right? This is an example where the average momentum is not equal to 0. And you can check out, right, that the average momentum divided by mass is, in fact, the time derivative of the average position, right? The same as it's supposed to be, right? And that all works because we're dealing with correctly normalized wave functions. And so that's the average momentum, and there's some average of momentum squared, and there's an uncertainty in the momentum that we can calculate. And then once again, we can check the uncertainty principle and say, what's the product of those two uncertainties? And look, it comes out to be a half h bar times something that's at least as big as 1, right? So that's consistent with the uncertainty principle. Okay, let me quiz you on something, right? This was an example where I have a particle that's moving to the right, okay? What if I wanted an example where there's a particle moving to the left? What would I change? Okay, can anyone tell me about that? If I wanted to just change something in this to make a wave packet that moves in the other direction, what could I change?
Maybe where you have like an expression of k minus k naught, it could be k plus k naught.
Yes, that's exactly right. Basically, what you're saying is that I could just change the sign of k naught, right? Where there was minus k naught, I change it to a plus k naught, and so that could work in a few different. I mean, I could enter that in a few different ways, right? So one is right up here, right? That's what you were just saying, right? That if there's an k minus k naught in here, I could change that to a k plus k naught, right? Or equivalently, in all of the examples, instead of putting in k naught as 10, I could put in k naught as negative 10, right? And so let's try that, okay? So if I'm going to do this movie, and I'll do the movie and I'll just put in k naught as negative 10 instead of positive 10, right? So let's make the movie again. And oops, it goes off the screen because I have the wrong range. Okay, let's do a bigger range of x. Minus 36 to 36, okay? Yeah, okay. So you can see now the wave packet is going the other way. And so here is the corresponding thing for the probability density. Oh wait, I meant to, that goes off the screen too. If I rescale it. Yes, so this is going to be a probability density that moves off to the left instead of to the right. And that makes sense in the equations, right? Because the average momentum is h bar times k naught, right? And so if I make k naught negative, then the average momentum will be negative, meaning that the particle will be moving to the left instead of the right. Let me show you one other thing that's kind of interesting in the graphics here. Let's take this probability density, and I'm going to replot it on the same axes as for my example number 1. Okay. So here's the probability density at time is 0 for example number 2. Okay. You can see it's a peak about the origin. Now let's go back to example number 1. Here's the probability density in example number 1 at t equals 0. It's exactly the same, right? It's exactly the same, right? That in these two examples, they start with the same probability density. They have different wave functions because of the complex phase factor, the e to the I k naught x, but they have the same probability density. Right? But you've seen, right, that what they do in the future is completely different, right? Example 1 doesn't move, example 2 moves, okay? So this should tell you that knowing the probability density at the beginning is not enough for solving a quantum mechanics problem, okay? Knowing the probability density is like in classical mechanics if you just know the initial position, okay? So suppose, in classical mechanics, in university physics, somebody tells you the initial position of a particle and they say, calculate what happens in the future, okay? You have to say, no, I can't. That's not enough information, right? It's not enough information to know just the initial position. You have to know the initial position and the initial velocity. Okay? So the same way in quantum mechanics, it's not enough to know the initial probability density. You also have to know the whole wave function. You have to know the real and imaginary parts of the wave function. Right? And here's a specific example of that, right? That in example 1, you have the initial wave function looks like this, okay? It's all real. There's no imaginary part. Okay? In example 2, where is it? The initial wave function, here, I'll put it on the same axes. In example 2, the initial wave function looks like this. Whoops. The initial wave function looks like this, okay? It's a different wave function, right? It's a different wave function which has the same probability density, right? Because the probability density corresponding to that initial wave function is like that, right? So a wave function has more information than a probability density, right? Because a wave function includes all the information about real and imaginary parts. Right? So if you know the initial wave function in quantum mechanics, that's like knowing the initial position and velocity in classical mechanics, right? And that's enough information. But if you just know the initial probability density, not enough information. Okay, so the phase stuff, the real and imaginary part stuff, it actually matters, right? And so this is a specific example where it matters. Okay, that is my story about the free particle. Okay, and so it's a story where the computation of the stationary states is not hard, but the what you do with the stationary states is maybe a little bit subtle, because you're not summing over them. You have to integrate over them instead of summing. But it's a related concept, summing versus integrating. Okay, so that's what I wanted to say about this problem. And on Thursday, I'm going to go on to one more one-dimensional problem, which is a delta function potential. And so we're going to need more delta functions. And so you should for sure review, if you need to review about delta functions, and ask me if you have questions about delta functions. All right, then. Let's stop here, and I will see you guys on Thursday. Thanks.